So as we were saying before, we can convert a real integral into a contour integral in some way. This is the part that is interesting to look into some examples or some types of integrals for getting this easily. But well, the important thing is that once we are talking about evaluating integrals. Sorry. Once, if we have a contour integral, well, normally it will not look irregular like this. It will look for, could be for example, a rectangle or whatever. If we have a contour integral, then on the complex plane, we know how to calculate this integral using the residue theorem. Just look at the singularities inside. And a line integral can somehow be represented as a real integral, because any line can be mapped to the real line, right? Or a segment of the real line. So here, each of the pieces of this integral could represent a real integral. And the sum of these pieces is equal to the total contour. So that's how we can convert from a contour integral to a sum of real integrals, a sum of these integrals of each piece of the contour. The example that we have seen last week, which only one circle, is the easiest case because there is only one piece of line, one piece of contour. There is only one circle. That means this is the simplest contour that we can have, just a circle, which is mapped to the real integral between 0 and 2 pi, as we have seen. So that would be the easiest case. But in general, we will have contours that have 2 pieces or 3 pieces or 4 pieces, like that, like a rectangle. So of course, this changing from a sum of real integrals to a contour integrals can be used to find one of these real integrals, but the condition is that we know how to calculate the other real integrals that appear there. So imagine here, if I say the contour integral will be, well, it would be the sum of 4 real integrals, right? And maybe one of them is the one that we want to know, but then it's important that we know how to estimate the other real integrals, because the contour integral is the easy part. We know we'll have a sum of residues, etc. So we know how to calculate the left-hand side, and on the right-hand side we need to know some of them, so we can evaluate the one that is interesting for us. So in many cases, let's say another very simple contour that we can use, and we use it a lot, but please notice that it doesn't mean we have to always use it. It is so you just have to check in each case. A contour that we use a lot is a semicircle contour, in which we go from some value, some real value, let's call it minus r, to the value r on the real axis. So the contour goes along the real axis. So it's very easy to change the variable to change between a complex variable and a real variable, because that would be just the real part of the complex variable. And then we go back to close the contour on a semicircle of radius r on the complex plane. Okay, this is, for example, this contour, let me call it gamma, is useful for several types of integrals. When we take the limit for larger and larger r, so when r goes to infinity, you have to imagine this semicircle getting wider and the segment on the real axis getting longer. But as I said, there are two line integrals, two pieces of contour here that can be represented as real integrals. So this contour is only useful, okay, it could be useful to find an integral, for example, an integral between minus infinity and infinity of a real variable, but only if the second part of the contour, the semicircle, can be estimated in some other way. If the integral around the semicircle is also unknown, then we cannot use this. Do you understand what I mean? It's not useful to say the contour integral is equal to the sum of two unknown real integrals, because we cannot find both unknown real integrals at the same time. But if we say the contour integral is equal to a real integral that we want to calculate, plus another real integral that we can estimate in some other way, if we know how to estimate the second integral, then this is useful because the left-hand side comes from the residues. This one we can estimate somehow, and then we get the integral of interest. Anyway, so one example of these, of a type of integrals that can be represented like this, is if we have two polynomials. Okay, let me call the two polynomials P and Q. Okay. So P and Q are polynomials. And we are going to check that in the case where the degree of Q is at least two larger than the degree of P, then we know how to estimate the semicircle part. So let's say, the polynomial degree of Q is at least 2 larger than P. Maybe you are wondering why 2. Okay, we are going to see why. But anyway, this is a type of integrals that can be very useful. So the change of variable is very obvious. Here the change of variable is just for the integral. Okay, first, the contour is going to be this semicircle with going from minus r to r and then back to minus r, and then along the x-axis we just use z equal x. Along the semicircle we can use, of course, a variable that goes along the semicircle, which is a complex number of modulus capital R and some phase that goes from 0 to pi, right? Okay, So let's write this. We know the sum of these two real integrals will be equal to the contour integral of this function, since we have just the polynomial of x, and this we can just use the polynomial evaluated at z. Okay, so the contour integral of this function will be the sum of the real integral over x between minus r and r of this evaluated on x plus the integral around the semicircle, which is an integral on theta, starting at 0 and ending at pi, right? Here we have to evaluate p at this r to the r times e to the I theta. We have to evaluate q also there. And then we have to multiply by dz. In this case, dz is just r times I times e to the I theta d theta, right? If you get confused with something, please let me know. So you have here dz is r I e to the I theta d theta. What's happening? Okay. So this is, as I said, an example where we separate this contour integral into two line integrals. Each line integral is an integral of a real variable, here x, here theta, and this could be done for any value of r, but we are interested on the limit when r goes to infinity, because then when r goes to infinity, this integral becomes this integral here. But yeah, the problem is what happens with this when r goes to infinity. So the thing that you have to notice is that, of course, e to the I theta is a complex number of modulus 1. So if I how to say, yeah, no matter what the value of r is, e to the I theta will always have modulus 1. And also, you have to notice that if I have a polynomial, for example, p, when the the variable of the polynomial, well, in general, z. Oh, well, imagine it like in real numbers first. So if the variable becomes larger and larger, of course, the polynomial will be a sum of terms in which the one with the largest exponent will grow faster than the others, and it will dominate the sum. So when r goes to infinity, this polynomial will be a complex number. Well, let's say a complex number that will have a modulus of the order of r to the n, with n is the order of the polynomial, right? Because the other terms will be smaller. The n minus 1 and minus 2 will grow more slowly. So the modulus of this complex number will grow like r to the n. And for the q, for the denominator also, this will be a complex number that when r goes to infinity will grow like r to the power of the order of q. So when you put these things together with this r, you will see that you will have here a complex number in this integral. in this integral, you will have a complex number that has a modulus. The modulus will be r to the order, how do we call the order of p? Sorry. Let me write it, order of p divided by r to the power of the order of polynomial q times r. Okay, that is why we said that the degree of q has to be at least 2 larger than the order of polynomial p, because here we will have this r. We can put this r as order of p plus 1 here, and this this will go to, so this will be a number with a modulus that goes to 0 when r goes to infinity. Of course, if the order of p plus 1 is less than the order of q. Okay, so for example, the p is a polynomial of degree 2. Sorry, I should say degree, not order. Well, you understand what I mean. The p has a degree 2 and q has a degree 4, then it's fine. Because still we'll have something that goes like r to the power of 3 divided by r to the power of 4, which goes to 0 when r goes to infinity. If the degree of q is only 1 larger than the degree of p, then we cannot assume this complex number will go to 0. It will go to some constant, and then in general there could be a complication, but in this case when r goes to infinity, so when r goes to infinity, this will be the integral between minus infinity and infinity, but the one that we want to calculate, and this will be 0. And the contour, so the only thing that we need to imagine is how the contour will change if r goes to infinity. But of course, when r goes to infinity, the contour will just get larger in every direction, and the semicircle will become an infinite semicircle, but the inside of the contour, let's say the inside of the semicircle, will become the whole upper plane. So we will have a line that goes from minus infinity to infinity, and we will have, okay, so the semicircle will be so large that basically everything on the upper half plane will be inside the contour. Everything on the lower half plane will be outside of the contour. That means we can just calculate the integral that we want. The integral between minus infinity and infinity of p divided by q will just be 2 pi I, the sum of the residues that have an imaginary part larger than 0. That means they are on the upper half plane. Okay. Sorry, I forgot the word. So all the residues of what? The residues of the function p divided by q at all the singularities j that have that are inside the contour, which are the points that have imaginary part larger than 0. Do you agree? And of course, since p and q are polynomials, we would expect the singularities of these p divided by q to be the zeros of the denominator. But just have to find the order of the singularity or the pole. So this will always be a pole. The order of the pole will depend not just on the order of the zero, but the zero of Q, but it would be the order of the zero of Q divided by P. So it's important you remember that this is always the function that you want to integrate is the two terms, P divided by Q. Okay, let's see a very easy example. Do you have any question?
No, not yet.
Okay, thank you. Let's see an example. So we want, I mean, this is an example of an integral that could be calculated in other ways, but it's just to start to a simple example. As I told you, the residue theorem is very powerful because we can use it to calculate some integrals that would be too difficult or even impossible using other methods. But this is not the case. This integral can be easily found using some other change of variable or noticing that, well, actually, as I said last week, the residue theorem is used for integrals that are definite integrals. That means with the limits well defined. But in this case, in some cases like here, we could find the integral by first taking the indefinite integral and then evaluating it at the limits. And in this case, yes, the indefinite integral of 1 over a squared plus x squared can be found as in terms of the arctangent. But okay, this is just an example. How do we do this? Well, again, we notice that we have a degree, a polynomial of degree 2 in the denominator, and of course the numerator doesn't have any x, so it's kind of 0. So if you check that, then you don't need to worry about the semicircle, because we have seen in the previous page. Well, I erased it already, but yeah, you can see that for any two polynomials, if the degree of Q is 2 larger than P or more, then the semicircle will go to 0. But it's important to check that, because if that's not true, then this method doesn't work. Now, since this is true, that means I can calculate this integral just by summing the residues of 1 over a squared plus z squared for the singularities that are have positive imaginary parts. So what are the singularities? What are the singularities of these functions? Let's practice again.
Plus and minus a.
Plus and minus a, are you sure?
IA.
It's almost
sorry, IA.
Yes, thank you. Perfect. IA, because this is a plus. Yeah, with a minus, it will change to plus and minus a, but there is a plus, so it's plus and minus IA. And of course, a is real, because this is a real integral. Well, we normally would specify it, but if we don't specify it, we should assume that this is a real integral, so a is a real number. So IA is a purely imaginary number. So that means, and then, well, if we assume a is positive, it doesn't matter, but it's the simplest thing. Then we'll have IA here and minus IA here. That means only one is inside the contour. Okay, so the contour, actually the contour, even when the contour doesn't go to infinity, we will have one singularity inside the contour and the other one outside. And this doesn't change when r goes to infinity. Still IA is inside, minus IA is outside. So we need to find the residue of 1 over a squared plus z squared in the point IA, which is the point that is inside the contour. How do I calculate this? Well, again, we don't need to check that these are simple poles because it's easy to remember that a polynomial of degree 2 will have two simple zeros if the zeros are different, and 1 0 for the two if the two zeros are the same. So these are two simple zeros of the denominator, and these are simple poles. So we use the simple pole method, and yeah, I think we saw this example. Yeah, we saw this example last week anyway. 1 over z squared plus a squared. We found that this residue is 1 over 2ia. Remember, the residue theorem tells me that I have to add all the residues inside the contour and multiply by 2 pi I. So when I multiply this by 2 pi I just get pi divided by a, and that is the result for any value of a. Okay. Any question? Okay, so maybe you can practice. Maybe you can practice this in the homework. Just remember this. This works with these conditions, that the limits are from minus infinity to infinity, and that we have only polynomials, and the degree of the denominator is 2 larger than the numerator or more. If these things are not true, then maybe there are other methods, but this method is only true like this. Okay, let me start a new page. Now, this is another example where we have also polynomials, but the integral is only from 0 to infinity. Let me remind you that in general, for any integral like this, or for any integral in general, you can sometimes use the method like this for a limit that is only half of the domain of the interval, if the function is even. Okay, if p is even and q is even, or actually if p is odd and q is odd, which combined together give an even function. So in only that case, which is very specific, then you could find the integral like this, from minus infinity to infinity, and divide it by 2. But this is only in the case where p divided by q is an even function of x. Let's see another case. Here, in general, if we have two polynomials that don't need to be even or odd, but the polynomials have only some terms. Let's write it like this. For example, n is some integer that actually it should be at least 3. So n is at least 3, an integer. What does it mean? So for example, p of x to the power of 3 means it's a polynomial where you can only have power of 3, power of 6, power of 9, something like that. So terms of x to the power of n as the variable for the polynomial. In this case, we don't need the degree of q to be too larger than p, but it has to be larger in basically the degree of q has to be, well, any and at least one larger than p. Okay. So let's see. Well, this looks very specific, but yeah, it could have some applications. Now, in this case, the change of variable and the choice of contour is not so obvious. So this is like some kind of thing that you have to remember. And please remember that every time you use the residue theorem, it's very important that you specify very clearly what contour you are going to use. For these polynomials of x to the power of n, the contour that works well looks like this. Okay, this is the real part of z, the imaginary part of z. And we can define a contour that goes from 0. Well, we will need this to go from 0 to infinity. But we are going to go first from 0 to a large number r along the x-axis. And then we will take the limit when r goes to infinity. And then we go at constant radius again, but instead of doing a full semicircle, we'll just do a sector along this piece of circle up to another point, and then go back to 0. Okay, this shape is useful for this integral as long as we take the size of this sector to be exactly 2 pi divided by n, the n that appears here, which, well, we said it's at least 3, but it could be as large as you want. Why is this sector interesting? As I said, we need to have a contour, let me call it gamma again, that can be divided into pieces, and each piece is represented by a real integral along the line integral is converted to a real integral, and this is going to be the contour integral. So to use it for calculating one of these real integrals, we need to know the other real integrals. In this case, we have 3 pieces, right? Here 1, here 2, here 3, and when r goes to infinity, the real integral of this side will be the one that we want to calculate. So what happens with the other 2? Okay, let's first, I mean, I'm telling you that this works, so let's see why it works. Let's first write what I said, the equality between the contour integral on this contour gamma. This is on the complex plane. We use the complex variable z. Okay. Remember, this is p of a power of z, dz. So it's just, we are just evaluating the same function. And let's write this as the sum. Now we have 3 integrals, right? The integral along the x-axis is very easy. We just do here z equal x. And this is the one that will become the the integral of interest when r goes to infinity. Then we have another real integral along the piece of circle. Of course, this is a real integral on theta very easily because the modulus of this complex number is constant, equal to r. So we just do the same as we did before. We integrate on theta. Now theta now will go only from 0 to this number 2 pi over n that we chose for the width of the sector. And we have to take, well, this polynomial. Well, remember z is this, but let me write it like this. Q, let me write it like this for simplicity. Just you will need to evaluate the polynomials at this value of r e to the I theta. Remember, there will be another r, another I, another to the I theta d theta. The important thing is that if the degree of Q is larger than the degree of P, and n is at least 3, that means the denominator will grow with a power of capital R, which is at least 3. Well, it depends on the degree, but yeah, the degree of the polynomial, not the degree of the polynomial of z, but the degree of the polynomial of z to the n is larger for Q. So the power of z will be at least 3 larger for Q than for P. So even if we have this R in the numerator, we will still have a function. When we evaluate this function, it will be complex numbers with a modulus that goes to 0 when R goes to infinity. So again, we are choosing the cases where this piece of circle will give a real integral, which is 0, because it's the integral of a function that has modulus 0. So this is fine. Now for the third piece, what is the change of variable that we want to do? Well, again, there are some easy change of variables along the, we are choosing the contour to make it easy. For example, z equal x, if we're going along the x axis. Now, a line that goes through the origin like this can be converted into how do I say, a real variable. The real variable can be the modulus of the complex variable. So if I take this to be a variable r, and now notice the argument along this piece of straight line, here, the argument is constant, right? So all this, the change of variable is very easy because the argument is constant, and it's e to the I 2 pi over n, right? This is the change of variable in which we can convert the line integral on the complex plane to a real integral. The real integral will start at r equal capital R and will end at r equals 0. And again, we will have to evaluate the polynomial on these powers of the complex variable z. But notice that when we evaluate a polynomial on this with z to the power of n, it will be the same as evaluated the polynomial at r to the power of n times e to the I 2 pi n divided by n, right? And this is of course 1 always. So this is just r to the power of n. So we can just evaluate the polynomial at r to the power of n instead of z to the power of n. Okay, and that is why this integral simplifies a lot. The polynomials are evaluated on only the modulus. We still need the dz. Well, the z is just dr times e to the I 2 pi over n, and we got this integral. So notice that here we have the sum of 3 integrals. Only one of them is going to be 0, but notice the other 2 are related because it doesn't matter if we integrate along x or along small r. The real integral will give the same value no matter how you call the variable. So what we see here is that when r goes to infinity, the contour integral of the contour integral of on gamma of these will be the integral between 0 and infinity of pxn divided by qxn dx times 1 minus e to the I 2 pi over n. Because notice the second integral will be the same, but multiplied by this exponential of I 2 pi over n. And it will be the sine of 2 pi over n, cosine of 2 pi over n plus I sine of 2 pi over n. And with the limits, because the limits are reversed, we have a minus. So in this case, you see, we don't know how to calculate these 2 integrals, but these 2 integrals are just the same integral multiplied by a constant. So we can just calculate the contour integral and divide by this complex number, which we know. And then we will get the integral that we want. Let's simplify this then. Is this clear? This is the type of trick that we use to get the real integral. So from this, we will get that the integral from 0 to infinity of the function that we have at the beginning will be the complex number 1 divided by 1 minus the exponential of I 2 pi over n, multiplying the contour integral. Okay, but the contour integral is just the sum of the, never forget the 2 pi I. It will be 2 pi I, the sum of the residues. Well, here the residues, notice that we want the singularities that are inside this contour, but the size of the contour will get larger and larger when r goes to infinity, but only between these 2 values of the argument. So when r goes to infinity, this will grow, but it will become like an infinite sector, but only for arguments between 0 and 2 pi over n. So we want singularities. So we want the singularities that have an argument between 0 and 2 pi over n. And of course, the residue will be the residue of this function here, p z n divided by q z n. Okay, let's see an example. Do you have any question about this?
What happens if the singularity is on the line of contour?
Yes, that's a very good question. We are, I can tell you now, but I was going to discuss that later. Well, maybe I will tell you the details later, but right now I can tell you that if you have a singularity exactly on the contour, you can modify the residue theorem, and in practice it's like adding half of the residue. So if a singularity is exactly in the contour, instead of summing the residue, you will sum half of the residue. But I will tell you why a bit later, okay?
Okay.
I mean, we can still treat it, but it's, I wanted to show you some examples first. I mean, we are now assuming that singularities are inside or outside. And later we will go back to your question. Thank you. What time is it? Okay. Well, let's see an example first. So let's see this example. The integral that I want to calculate, very, probably one of the easiest cases of this form. We have the integral of 1 divided by 1 plus x cubed. By the way, this integral looks very innocent, but if you try to calculate it with other methods, it can be tricky. Now, with this type of sector contour, this is very easy. Remember, here we have, so let's say here we have p of x cubed of degree 0, because it's just the number 1. And here we have q of x cubed of degree 1, okay? Notice a polynomial of x cubed will be something like a constant plus a1 x cubed plus a2 x to the 6 plus a3 x to the 9, things like that, right? But here we don't have, we have only the a1, right? So it's degree 1. So degree 1 is larger than degree 0. This method works. And well, you can do the sector again, but we just can, since we just did it, we just can simplify. Notice that the contour here will have 2 pi divided by 3 shape, so it will be more like this. What is, will go along the x-axis. Okay. And then 2 pi divided by 3 looks like this, right? Something like this. So it will be, if I am correct, it will be something like this. And we will have, but since the argument here is 2 pi divided by 3, then the integral along this and the integral along these lines are the same multiplied by a constant. So we can just, I did something. Okay, never mind. Anyway, so we will have what I was going to say. This angle is 2 pi over 3. And the constant that we need to calculate is, okay, so let's substitute from this one. So the integral that we want to calculate will be 1 divided by 1 minus the exponential, you see, of I 2 pi over 3, and then the sum over the over the singularities. It's very important to remember the 2 pi I. The residues of the function 1 divided by 1 plus z cubed, but only for the singularities inside the contour. So we need to have the principal argument of the singularity between 0 and 2 pi over 3. So first, what are the singularities of the function? What are the zeros of the denominator? Because notice the function is otherwise analytic. So what are the roots of this cubic polynomial? Who can tell me? Well, it's a cubic polynomial, right? So it should have three zeros, 3 simple zeros, or whatever. It could have some multiple zero. In this case, it has 3 simple zeros. Who can tell me which ones? Well, let's. I think you know it, but okay, let's solve it. It's very easy. If we take z cubed equal -1 and we write it in polar form, so r cubed e to the I 3 theta must be equal to e to the I pi. And either on the right or no, on the right or on the left, we have to add any multiple of 2 pi. So for these numbers to be equal, that means the modulus have to be equal to 1. And 3 theta plus 2 pi n must be equal to pi. And this gives me theta can be pi divided by 3 plus or minus, that doesn't matter because it's an integer, 2 pi n divided by 3. And remember, from the infinite possibilities of n, there are only three values that will be different on the complex plane, and they will form a triangle, right? We discussed that the other day. I'm just repeating it in case it's not clear. So, but okay, from that, it's easy to see that for n equals 0, we have z equal to pi over 3, right? Sorry, exponential of I pi over 3. Sorry, the argument is the modulus have to be 1 to the e to the I pi over 3. If I add 2 pi over 3 to this, it would be 3 pi over 3. So it would be just e to the I pi, which is -1. That would be for n equal 1. And for n equal 2, it would be like, we can write it as 5 pi over 3, which is actually the same as minus I pi over 3, right? So yeah, we have, let me remove this thing, let me remove this here. We have one singularity. On the 3 are on the unit circle, because the modulus is 1. We have 1 here, and 1 here, forming a equilateral triangle. As you can see, only one of them is inside the contour, right? When the contour goes to infinity, the shape of the sector is the same. It just gets larger on the R side. So this one is inside, right? This e to the I pi over 3 is inside. These two are outside, so we don't care about them. Or just look at the argument. The only argument between 0 and 2 pi over 3 is pi over 3. So we just need to calculate the residue of 1 over 1 plus z cubed at e to the I pi over 3. Who wants to do this for me? And of course, it's a simple poll. Do you agree?
Yeah, agree.
Okay, so what method would you use? I think L'Hopital here is the easiest, right? So we don't have to factorize the cubic polynomial. Using L'Hopital, sorry, I need a bit of space. Using L'Hopital, then we will have the denominator without changing divided by the derivative of the, sorry, the numerator divided by the derivative of the denominator, right? Evaluated at this. I think it's like this, 2 pi over 3. The square of that, 3z squared, evaluated at that. Okay, so we already have everything we need. But it's very important to simplify because we have a lot of complex numbers here with different things, but we know the result is going to be real. So just let's take the effort to simplify it to be useful as a result. So we have 1 minus e to the I 2 pi over 3. I'm just copying from this part here. And then the sum of the residues is just one residue, we just calculated, that is 3 e to the I 2 pi over 3. As I said, this is the result, but you should not give this as a result because it looks like a complex number and it's actually a real number if you simplify it correctly. Okay. How? Well, first you have to notice that first you have to notice, put here, that that the denominator yeah, it's 3 e to the I, too close to the e to the I 2 pi over 3. This is this multiplied by 1 minus this 3 e to the I 2 pi over 3 multiplied by this would be minus 3 e to the I 4 pi over 3. How do we simplify this? Well, we just need to notice that, okay, let's write it here. For this, in this type of things, we have the sum or the difference of exponentials. We need to find a way to convert that into a sine or hyperbolic sine or cosine or whatever. In this case, this would be related to the sine. Why? Okay, sorry. So we will have e to the I 2 pi over 3 minus e to the I 4 pi over 3 is just the same as the yeah, let's take out the factor of oh, well, no, we don't need to take the factor. Notice that, yeah, remember a number with argument 4 pi over, a number 4 pi over 3 is the same as a number with an argument of 4 pi over 3 plus or minus, in this case, plus or minus a multiple of 2 pi. So what happens if I say minus 2 pi here? 4 pi over 3 minus 2 pi, which is like 6 pi over 3, is minus 2 pi over 3, right? So this number is the same. Remember, the same point on the complex plane, that means the same number. This the exponential of I 4 pi over 3 is the same as the exponential of minus I 2 pi over 3. And then we know that this divided by 2I is the sine of 2 pi over 3. Right, so this is how we simplify this expression. We will have 2 pi I divided by 6 times I, the sine of 2 pi over 3. And the I cancels the I. So at the end, we get a real number. Okay, let me write this for the record. The exponential of I 4 pi over 3 is the same as the exponential of minus I 2 pi over 3. The same point on the complex plane. And well, this can be simplified if you just remember the sine of 2 pi over 3 or 120 degrees, I think. We get the square root of 3 divided by 3, I think. Well, in the end, we get a very real number, very specific real number, 2 pi divided by 3 square root of 3. Okay. And that is the value of this definite integral, which, as I said, if you try to calculate it with other methods, it can be a bit much more difficult. Let's take a break. Do you have any question?
Can you explain why the n is at least 3?
Yes. So what? Yeah, that's a good question. What happens if n is only 2? So if n is only 2, which yeah, I remember now. N could be 2. Yeah, but if n is only 2, it's easier to do it like this. Notice that if n is only 2, the contour will look like this, because we will have here 2 pi over 2, which is just pi. So the contour will be a semicircle. And if n is 2, we'll have a polynomial of x squared divided by a polynomial of x squared. That means the function will be an even function. Okay, maybe I should write that as a note. So yeah, if you have a polynomial of x squared divided by a polynomial of x squared, you can just calculate more easily the integral between minus infinity and infinity and divide by 2, because the function will be even. Do you understand what I mean?
Yes.
So that's why I was not including it. this is useful. It's not, sorry. It's not that it must be at least 3. It's that it's only useful if it's at least 3. If it's only 1, then it doesn't really work, because notice, due to this R here, the piece around the circle maybe doesn't go to 0. If n is 2, then it works, but it's a bit more complicated than the previous method. The previous method can be used because for the previous method goes from -infinity to infinity. But if if n is equal to 2, that means all the terms in the polynomial are even terms, and the function is an even function. So it's easier to use the method of the semicircle and divide by 2 instead of finding these. Well, this number will also be easy, but okay, this fun. It will be the same. Actually, the method would be exactly the same. You will need to include the same residues and everything, so the result will give you the same amount of work probably. But yes, to clarify here, I said n at least 3 because we don't need a special method for n equal to, since that would be the integral of an even function, and we can just calculate it from -infinity to infinity and divide by 2. Actually, that's true also for n equal 4, n equal 6, and now that I think about it. So yeah, I guess this is only useful for when n is odd. Yeah, because if the polynomials are of a function of a power of x that is even number, like 2, 4, 6, then the two functions are even, and then I think in those cases it would be easier. So let's write it here. If n is even, it's easier to just take the integral between -infinity and infinity. And since the function is even, the integral from 0 to infinity will be 1/2 of that. Okay. And I think it would be, well, maybe not easier. It would be more or less the same. Yeah, you can choose. So in this case, there is some overlap. Thank you. Any other question? So I'm going to take a. Okay. So the next type of integral has a special significance. Let's write it. So let's write this type like this. Now, if I have an integral between -infinity and infinity of any function, phi, multiplied by a complex exponential. Okay, this look a bit different because now, of course, this is a is a real number, but there is an imaginary unit here, I. That means the result of this integral is not real. Okay, but remember the exponential of a purely imaginary number. So if a and x are real, this is the exponential of a purely imaginary number, is the cosine plus I times the sine of the real number, in this case ax. Actually, this type of integrals have some interest because you can use this to calculate the Fourier transform, which we will talk about the Fourier transform much later in the course. But the Fourier transform can be defined like this, as the integral of a real function multiplied by this complex exponential. In that case, a, instead of a as a constant, we can evaluate that with a variable, some kind of frequency omega or something like that instead of a. But this is a general type of integrals. Let's assume first that a is positive, but if a is negative, we can just change a little bit. So this type of integrals sometimes diverge. So sometimes you cannot calculate it, but sometimes we can use the residue theorem with a semicircle contour like we did before. So if I write the axis more beautifully, if I write again the contour from minus r to r and then back along this part, let me call this part of the semicircle, this part of the contour, let me call it semicircle CR of radius r. So these integrals sometimes can be calculated, but to know if we can use the contour that I'm showing you or not, we need to look at a lemma that was formulated specifically for this. It's called Jordan's lemma. So before we do it, we need to check if Jordan's lemma is satisfied or not. So Jordan's lemma says, if I have a function, a real function phi, Jordan's lemma is for the complex variable function phi, which is going to be the same function but evaluated on the complex plane. So if this function is analytic in the upper half plane, except on a finite number of singularities or poles. It's okay, it doesn't need to be analytic everywhere, but the number of poles is not infinitely many. So if the function here needs to be analytic on the upper half plane, okay, with the imaginary part, a positive imaginary part, and if the value of the function vanishes, goes to 0 for a variable that has a very large modulus, only on the upper half plane. So they'll say, but for all the values, well, including 0 and pi, so for the argument of z between 0 and pi, then the limit for the size of the semicircle going to infinity of the line integral only around the semicircular parts, okay, not the closed contour, but only the semicircle on the upper half plane of the function of the complex variable along that semicircle times the complex exponential with the complex variable also, is going to be 0 if A is positive. Okay, this is a Jordan's lemma. So it says very clearly in what cases the line integral along the semicircle can be estimated because it's going to be 0. So in that case, we can use the same method as we have seen before. We can calculate the integral only on the x-axis by taking the integral along the contour and noticing that it's the sum of that that integral on the real axis plus the integral that goes to 0. And if A is negative, actually we can just, what we will do, if A is negative, what we will do is we will do the contour like this. We could do the contour from minus R to R and taking the semicircle. I mean, this semicircle is, this contour is going to be counterclockwise. So we will just add a minus somewhere. But anyway, the interesting thing is that if this is CR, the Jordan's lemma can apply instead of upper, the lower half plane. Okay, and here instead of 0 and pi, we'll have pi and 2 pi, for example. This lemma is also true if A is negative, but we would use this other contour. Okay. Well, let's assume A is positive. And as I said, this integral can be solved like this. So notice that this part of the function is going to oscillate, right? It's like sines and cosines. So when x is larger, this oscillates faster. So so it's not clear, just by looking at this, it's not clear if the integral is going to converge or not. But Jordan's lemma is telling us that yes, it converges as long as this function goes to 0. Then, well, you have to imagine this thing is just going to add, or let's say to include some argument that oscillates between -1 and 1, for example, for the cosine, between -1 and 1 for the sine. So it's like a number on the unit circle, and that doesn't change the fact that this integral goes to 0. I'm not going to prove Jordan's lemma, but it's important to base our method on assuming that Jordan's lemma is true. And notice that here phi, the function phi can be any function, not polynomial or anything. The only important thing is that the function goes to 0 for large z. And well, it doesn't need to go to 0 for every z, only for the z on the upper half plane or lower half plane when the modulus goes to infinity. Okay. Now, another interesting thing about this integral with a complex exponential, is that we can calculate, express, for example, an integral like this. If I have an integral like this, since the cosine of AX is the real part of the complex exponential, then I can calculate the integral and then take the real part. So the integral of this is also the real part of the integral that I am talking about. So this is what is also useful to calculate real integrals, in which we have some function multiplied by a cosine. If the function goes to 0 at large x. Well, sorry, it has to go to 0 at large z for arguments between 0 and pi. So find the integral first, and then take only the real part. And that will be the same as the integral of the function times the cosine. If we need a function times the sine, then we take the imaginary part. This is clear. So just calculating this integral is going to give me automatically these two integrals. Okay, these two integrals come from just calculating one integral of phi times exponential of pi ax. I just need to take the real part or the imaginary part of the result. But I think this is easier to understand with an example. Do you have any question? Okay, so let's look at this example. If I want to calculate the integral between 0 and infinity of the cosine of some number times x, now here I'm calling it m, divided by another number x squared plus x squared. Okay. And I need to know if the number in the cosine is positive or negative. I'm going to assume it's positive. And if, well, the number A doesn't matter, but okay, I'm going to also assume it's positive. So m and a are real. So in this case, this integral should give me a real number, right? Now, but the limits are not minus infinity and infinity. However, this is something that is always useful to check. We can check that this is an even function, right? The cosine of minus mx is the same as the cosine of mx, and minus x squared is the same as x squared. So the going from 0 to infinity and from minus infinity to 0, I get the same value. So I is 1/2 of the integral from minus infinity to infinity. But notice that also the integral from minus infinity to infinity of this function is going to be the real part of the integral from minus infinity to infinity of the exponential of I mx divided by a squared plus x squared. Do you agree? So that's why this is, with this type of integrals, we can do many other things. Not, I mean, in some cases. So it's important to recognize that this is because it's even, and this is because it's a cosine. But in the end, we just calculate this integral and take the real part and divide by 2, and then we get the integral that we want. Now, let's check Jordan's lemma. Does Jordan's lemma apply? Jordan's lemma says I have a function phi. So here phi would be 1 divided by a squared plus z squared. Okay, phi will be 1 divided by a squared plus z squared. This is a complex number that is easy to see that goes to 0 when the modulus of z grows larger and larger. Do you agree? Because we'll have, well, it will be a complex number that has a modulus which will tend to be closer and closer to 1 divided by the modulus of z squared. That grows, this modulus goes to 0, and then this function goes to 0. Actually, here, actually, in this case, it doesn't matter if we imagine the argument of z between 0 and pi on the upper half plane, or the arguments of z larger than pi. It's true for any argument, actually, but in general, you have to consider if the function goes to 0, that goes to infinity for the specific case of all the values of the argument of z between 0 and pi. So when the modulus goes to infinity for the arguments between 0 and pi. As I said, in this case, really, it doesn't depend on the argument, but in general, this is what Jordan's lemma is telling us. Jordan's lemma is also telling us that function phi needs to be analytic, except for a finite number of poles, and that is true. Of course, we have 1 divided by a polynomial that is analytic everywhere, except on the zeros of the polynomial. So yes, Jordan's lemma is true. If Jordan's lemma is true, then I can take the integral between minus infinity and infinity of exponential of imx divided by a squared plus x squared is going to be the same as the contour integral along the total contour gamma, including the x-axis and the semicircle, when r goes to infinity, of the same function evaluated on the complex variable, right? Because the part of the semicircle is 0. So the sum of the two line integrals is going to be only this integral, because the semicircle is going to be 0 when Jordan's lemma is satisfied. Okay, so very easy. We just need to find what singularities of this function are inside that infinite semicircle, if you want, and calculate the residues, multiply by 2 pi I. Okay, so of course, the numerator is analytic everywhere, has no singularities because it's just an exponential. So we know the singularities are the zeros of the denominator, which are remember? Well, actually, this is the same that we have seen before, right? The same function that we have calculated a couple of times already. The zeros of this function, a squared plus z squared, it's even called the same. So we can go back to page 2 and we can see there are two singularities. And since the numerator is analytic, the exponential of imx is analytic and it's not 0 at this point, then the singularities are the same 2 points and also simple poles. So again, the same as in this example, IA is inside minus IA is outside. Now, to calculate the residues, instead of 1 divided by a squared plus z squared, it's very important the residues has to be calculated with the total function. So we need to find the residues of the exponential of imz divided by a squared plus z squared at IA. IA is the only singularity inside the contour. But remember, for the residues, you need the full function, not separate the function into components, because the residues is a property of the thing you want to integrate. So don't forget the numerator here. And of course, again, multiplying by z minus IA and taking the limit, we get the same as before, but with the exponential of IM multiplied by IA. Okay, so it's I squared minus multiplied by M multiplied by A. And then the denominator will be the same as before, 2IA. So what you get when you take the limit when Z goes to IA, right? So this is the residue. This is the residue. So that means this integral is 2 pi I exponential of exponential minus MA divided by 2IA. The 2 and the I disappear. So, okay, so this integral is pi divided by A exponential of minus MA. And the integral that we want is 1/2 the real part of that. But notice that here M and A are real. That means the real part, I mean, this number is already real. So the real part of this number is the same number. So we will get like that, pi divided by 2A exponential of minus MA. That is the result for this integral I. Any question? And this is true for any M and any A. With non-zero A, of course. Okay.
Teacher.
Yes.
Sorry. At 5 line. In I am set and it is the set or the x.
Yeah, you are right. Yes, thank you. I was doing it too fast. This is the set. Yes, thank you.
Okay, thank you.
Because yeah, so the contour integral, can explain, and well, remember we do always the same, right? This is on the complex plane, and that is the sum of the line integrals. But from the Jordan lemma, the sum circle will be 0. So so we just have the integral of x equal to the integral of z along the full contour. Thank you. Everyone is following this? Do you have any other question? So, okay, so let's see the other typical case. So here we have seen some typical cases where a semicircle is a good choice of the contour. The choice of the contour is a bit, you see, it has to be a bit of a clever choice. You cannot just choose a random contour because in general, maybe what you are trying to calculate doesn't appear from that contour. So we always need to choose the contour that will make things cancel or something goes to 0 or anything in which we can like find the equation between the unknown integral that we want to calculate and the contour integral that we know how to calculate by residues. So there is another type of integral like another prototype of integrals, which is when you have some exponential in the denominator of the function. So let's think a bit about what happens if we have some exponentials in the denominator. So, well, the function, you can imagine any function. It could be analytic, or it could be other, it could have other singularities. But if there is some exponential in the denominator, that means that there will be more singularities for the zeros of the denominator. That means for the values that make the exponential to be some specific value, the value that makes the denominator equal to 0. Now, the problem with that is that there are always infinitely many values that make the exponential equal to something. So the denominator will be 0 in an infinitely large number of singularities. So the contour has to be chosen. So okay, so what happens if we choose a contour like the semicircle before? If I try to use a semicircle contour, but imagine there are infinitely many singularities like this, for example, on a line. Well, there are several complications. One is that depending on R, the number of singularities will be different. When R increases, the number of singularities increases. And also that to calculate the integral by the residue theorem, we'll have an infinite sum. All of these things are bad, right? So this type of contour is not good for integrals or functions that have exponentials in the denominator. What you need for this case is to take a contour in which the number of singularities inside is constant, or let's say it's limited by some by the shape of the contour. Even if you take one of the sides of the contour to go to infinity. Let me summarize this here. So in general, this is the general case. We must choose a contour with a finite number of singularities inside. Typically, this is going to be a rectangle. So yeah, exponentials in the denominator will almost always need to be treated by taking a rectangular contour. Now, the problem with the rectangle is it has 4 sides, right? So the contour integral will be the sum of 4 integrals. So here, really, you need to choose the size of the rectangle in some clever way, because we don't want to have 4 line integrals that are unknown. We just want to have one unknown and have some way to estimate the other 3. Otherwise, it's not useful. Okay. So, sorry. But the idea is, for example, if the singularities are on a vertical line in the complex plane, okay, let's see, for example, if we have many singularities on the imaginary direction, one contour that we could use could look like this. going along this line, back and back, close contour, and then taking the rectangle, to go to infinity, something like that. We could, if we make this rectangle longer and longer, and all the singularities are on a vertical line, then the number of singularities inside will always be 1, for example, or 2, or whatever we choose. So so this shape removes that problem. That's not a problem anymore. What is a problem now is that we have, as I said, 4 line integrals. So so we need to see what happens with these 4 pieces. But there is no completely general method for this, so I think it's good to learn from the examples. I'm going to give you an example. And of course, if you have the singularities on a horizontal line, then you will need to have a rectangle going up and down. But sorry, I forgot to mention, please remember that exponentials, when I say exponentials, this includes sines and cosines and hyperbolic sines and hyperbolic cosines. Any trigonometric or hyperbolic function is actually a combination of exponentials. So if these are in the denominator, there will be infinitely many zeros of the denominator. Well, the easiest case to understand is if you have 1 divided by a cosine, the cosine will be 0 for pi over 2, 3 pi over 2, 5 pi over 2, etc. And all of these will be singularities. In that case, that will be along the real axis. So yeah, you have to adapt this method to the exact function that you are treating. Let's analyze one with a hyperbolic function. So imagine the integral that I want to calculate is the integral from minus infinity and infinity of an exponential of a multiplied by x times the hyperbolic secant of x. Now, where is the exponential? Okay, there is exponential here that is not in the denominator. Okay, this is in the numerator, but the hyperbolic secant, remember, is 1 divided by the hyperbolic cosine. So this is 1 divided by exponentials, a sum of exponentials. Now, actually, this integral is not going to converge unless, I'm not going to prove that, but I'm going to assume that a is a real number between -1 and 1. Okay, it has an absolute value less than 1. Remember, a is real, so this is absolute value. So I think we already found that the hyperbolic cosine of z is 0 for, we already found this, right? The hyperbolic cosine of z is 0 when the exponential of z is equal to the exponential of is equal to minus the exponential of minus z. We did that the other day, if I remember correctly, and any integer multiplied by pi over 2i is a 0 of the hyperbolic cosine. And since the hyperbolic secant is 1 divided by the hyperbolic cosine, then the zeros of the hyperbolic cosine are the singularities of this function. Notice that it's multiplying this other exponential, which is always analytic everywhere. So the zeros of the hyperbolic cosine are going to be singularities on all of them on the imaginary axis. Okay, so you have only for odd n, okay, not for all n. So for n equal 1, 3, 5, so there will be pi over 2i, 3 pi over 2i, 5 pi over 2i. These are, like I was showing here, they are on a vertical line. Okay, so let's zoom for this specific case. let's zoom near the x-axis. Near the x-axis, we will have, for example, one singularity here at pi over 2i, another singularity here at minus pi over 2i. The next singularity will be at 3 pi over 2i. And these points look like they look like the same as the letter x. So let me use a dot better. Okay, and then there will be infinitely many going up and down. And I want to find a rectangle. Okay, I want to create a rectangle that includes a finite number of singularities. So let's try if we can include only one singularity. That would be the easiest thing. Now the rectangle has to be infinitely long, but let's take it first to be just kind of long between minus r and r. R can be a large number. But then to have a closed contour, I need to go here from this point z equal r to a point that I'm going to choose exactly between these two singularities to be r plus I pi. So the real part is r, the imaginary part is pi. And then here I will go back to this point, which is minus r plus I pi in this counterclockwise direction. And then I close the contour like this. Okay, this is the type of rectangle that we can use. But as you see, now the problem is, what do I do with the 4 pieces? One of the pieces is going to become I when r goes to infinity. But how about the other 3 pieces? Okay, let's see what happens with this choice. Notice I didn't choose it really randomly. You just need to realize at the end how this choice is really the necessary choice. So here, if I call the total contour gamma, as usual, the contour integral of this exponential on the complex plane, instead of hyperbolic secant, let me write 1 divided by hyperbolic cosine of z. This will be the sum of 4 integrals. Okay, let's start with the x-axis integral before taking the limit. So it goes here, the change of variable, very easy. Z is the same as x. The line integral becomes the real integral between minus r and r of this function with x as a variable. Okay, this is the horizontal piece on the real axis. Then there are the 3 pieces. The second piece, let's take it from this point r on the real axis to this point r plus I pi, the vertical piece on the right. Now that is a line integral on the real variable y, right? The imaginary part of z. So I can just say z is equal to iy, and y starts at 0 and ends at pi, right? So here we have to see that, z is r plus iy, right? So here we have the exponential of a times r plus iy divided by the hyperbolic cosine of r plus iy, and this z will be I dy. Then we have to go on the horizontal piece from r plus I pi to minus r plus I pi. So again, it's an integral along x, but now starting at r, ending at negative r, and z here is x plus I pi, right? Sorry, there is an a here. A x plus I pi. I'm not going too fast, right? Hyperbolic cosine of x plus I pi dx. And the final piece going down vertically, again, is an integral along y, starting at pi, ending at 0. And now the exponential will be minus r plus iy. Probably cosine of minus r plus iy dy. Sorry, I ran out of space. Okay, you see what I'm doing here, right? I'm just changing. There is an I here. I'm changing the variable from z to x, from z to r plus iy, from z to x plus iy, plus I pi, sorry, and from z to minus r plus iy, because those are the values of the complex value, of the complex variable along these 4 pieces. Let me see. What happens when we take r going to infinity? That's the interesting thing, of course. The first of the 4 line integrals will become the integral I. That's fine. How about the other 3? So let's see what happens on the other cases. First, let's take, in general, the hyperbolic cosine for any x and y. Remember, we are going to have the combination r plus I times variable y, variable x plus I times pi, minus r. Okay, we have several combinations here, but x and y are real. So we can go to the properties of the hyperbolic cosine and remember that this is equal to the hyperbolic cosine of x times the cosine of y plus I hyperbolic sine of x times sine of y. Why is this useful? So notice, remember, we have a vertical piece where we have r plus iy, for example, and r is going to go to infinity, right? Sorry. Yes. So when r goes to infinity, the hyperbolic cosine and the hyperbolic sine are both going to go to infinity. And the hyperbolic cosine of r and the hyperbolic sine of r will grow. Let's say both for positive and negative r, but let's see for positive r. So we'll have the exponential of a r plus iy. Notice that here y doesn't matter too much because r is growing a lot. And here divide by the hyperbolic cosine of r plus iy. This will grow like the exponential of ar divided by the exponential of r, because remember the hyperbolic cosine here and the hyperbolic sine here will have an exponential of r and an exponential of minus r. When r goes to infinity, the exponential of minus r goes to 0. And this goes to, it will grow very fast as the exponential of r. Now, since a, we said, is between minus 1 and 1, then this will go like the exponential of a minus 1 r, right? And a minus 1, that means a minus 1 is going to be less than 1. Less than 0. If a is negative, of course, it's negative. If a is positive but less than 1, a minus 1 is negative. So for this vertical line between for y between 0 and pi, when r goes to infinity, this thing will go to 0 when r goes to infinity. And for the other vertical line, minus r plus iy, sorry, it's actually going to be the same, because the hyperbolic cosine, as I said, the hyperbolic cosine will have an exponential of r and an exponential of minus r. So the big one would be, again, the exponential of r. So these two vertical integrals for the integral along y, both of them will tend to 0 when r goes to infinity. So that's good, and that's why this doesn't work if a is not between minus 1 and 1. So we only have the third integral. So let's see the third integral. We have the exponential of x plus I pi divided by the hyperbolic cosine of x plus I pi. Now, see, we have x plus I pi. Then what do we have? We have the cosine of pi, which is minus 1, sine of pi, which is 0. Here. So that means the hyperbolic cosine of x plus I pi is easy to see, that is just the minus hyperbolic cosine of x. Okay. And we can write, remember, we had the limits reversed from r to minus r of the exponential of a x plus I pi divided by hyperbolic cosine of x plus I pi dx. I'm going to reverse the limits from minus r to r and change this to hyperbolic cosine of x. Because of this minus, I can reverse the limits. And then the exponential of ax plus ai pi, I can just put the exponential of ai pi outside because it doesn't depend on x, multiplying by the exponential of ax. Why am I doing all of this? Well, because notice that when r goes to infinity, this integral just converges to this constant, exponential of or ia pi, times the integral that we started with, okay? Exponential of ax divided by hyperbolic cosine of x. So that means I can calculate these both horizontal lines are the same integral, just multiplied by two constants. It's similar to what we did with the sector of the circle contour, in which we had two lines that actually depended on the same integral. So we can summarize here from these four integrals. From these four integrals, we will have, sorry. Let me move this here. From these four integrals, we will have that this one was 0. This one is 0 when r goes to infinity. When r goes to infinity, this integral is I when r goes to infinity. And when r goes to infinity, this other integral is the exponential of this times I. Okay. In other words, we have 1 plus this number times I. So that's what we needed to do. Find this integral and divide by this number. Okay, let's do it quickly. It's almost time to go home. Oh, it's already time. Okay, sorry. Let me finish this, and then you can see the result. Well, there is this one is 2 pi I. There is only one residue. We need to find the residue of the exponential of AZ divided by hyperbolic cosine of Z in the only point that is inside the contour, which is pi over 2I. And I let you check. I think we did something similar before. Remember that we put the full function here. The residue is, so we have 2 pi I, and the residue is minus I exponential of IA pi over 2. You can calculate it again if you want. And that means my integral is this 2 pi I times minus I is just 2 pi, exponential of IA pi over 2, and then divided by 1 plus the exponential of IA pi. And again, this should be real, so it has to be modified. But just you multiply by this with a minus, the exponential of minus IA pi over 2 in the numerator and the denominator, and you will find that you get a hyperbolic cosine in the denominator. Okay, in the end you get pi times the second, sorry, not hyperbolic, it's just a normal cosine because it has the I here. So you have the second of A pi over 2. Very simple and elegant result. Okay, any question?
From the, I have a question on the contour integral that is equal to 1 plus something. Oh, yeah. It's on the last page. Where is the 1 come from?
Yeah, sorry. So here we have, yeah, let me put the details. Yeah, sorry, it's a bit fast. So we have 4 pieces, and the first piece is I, the second piece is 0, the second piece is this exponential of II pi I, and the 4th piece is 0. Sorry, too small. You know what I mean, right? So we have two pieces that are related. So this piece gives me an I. Sorry, it's slow. This piece gives me an I, and this piece gives me that constant times I. And the other pieces give me 0. So we can write it. We can write it like this. We can write it like I plus 0 plus, you can see exponential of IA pi multiplied by I plus 0. And then I put together the 1 from this and the exponential of IA pi from this is just the sum. Sorry, this is an I. Is it clearer now?
Yeah, it's clear now.
Yeah, thank you. Any other question? So do you think you can practice this for your homework?
Yeah, I think I can.
So practicing is the best way to understand it. Okay, thank you. I